Although their names are interchangeably used, cement and concrete are entirely different products. In fact, cement is one of the primary raw materials used in the production of concrete, along with water and aggregate. The process of concrete making starts with making cement, the crucial binding material that holds the water and aggregates together in concrete. There are many different kinds of cement, but the most commonly used is...
Today's topic is cement. As we know, cement is a binder. When used in construction, it sets, hardens and adheres to the other materials so that it binds them together. Cement is derived from a Roman term called opus cementitium, which describes masonry resembling modern concrete, made from crushing rocks with burnt lime as binder.
The Egyptians were using early forms of concrete over 5,000 years ago to build pyramids. They mixed mud and straw to form bricks and used gypsum and lime to make mortars. And concrete was widely used in the Roman Empire. Romans discovered that adding volcanic ash to the mix allowed it to set underwater. The Romans used concrete extensively from 300 BC for more than 700 years. During the Roman Empire, Roman concrete, or opus cementitium, was made from quicklime, pozzolana, and an aggregate of pumice. It freed Roman construction from the restrictions of stone and brick material and allowed for revolutionary new designs in terms of both structural complexity and dimension. In 1824, Joseph Aspdin invented the modern Portland cement. He named his cement Portland after a rock quarry that produced very strong stone. In 1849, Joseph Monier invented the reinforced concrete. Reinforcing schemes are generally designed to resist tensile stresses in particular regions of the concrete that might cause unacceptable cracking or structural failure. In 1908, Thomas Edison designed and built the first concrete homes in Union, New Jersey. These homes still exist today. Edison envisioned that his design would meet great success and that before no time, everyone in America would be living in a concrete home.
Bahay, pinatibay ng Holcim Cement, Holcim Excel para pangbuhos at Holcim Wallrite pang asintada at palitada. Sa tibay at tipid ng combo na to, walang masasayang. Holcim Cement, building a better future together.
Pagdating sa semento, tiwala ang mundo sa eksperto. Cemex, the cement expert.
Ng Pinas, higher ang Eagle Cement. Sa standard ng mundo, higher ang Eagle Cement. Sa compressive strength, higher ang Eagle Cement. Eagle High sa tibay. Eagle High sa tibay.
At ulan. Kaya nangangalawang ang steel bars na pwede kasira ng konkreto. Pinupunan ng tibay enhancers ang mga butas para masiksik at matibay ang konkreto para maipapamana pa ang bahay na tinatayo nyo. Republic Cement.
There are many different kinds of cement, but the most commonly used is ordinary Portland cement. The primary raw materials used in cement production are limestone and clay. They are typically obtained from quarries by blasting or using heavy machinery to extract them from the Earth's crust. The extracted materials are transported to the crushing plant, where they are crushed into smaller pieces. The crushed limestone and clay are then mixed in appropriate proportions to form a raw meal. The raw meal is transferred to a mill, which consists of a large rotating cylinder. Inside the mill, the raw materials are ground into a fine powder. This grinding process enhances the efficacy of the subsequent chemical reactions and ensures the uniformity of the raw meal composition. The powdered raw meal is then heated in a preheated tower, where hot gases from the kiln are used to raise the temperature. As the raw meal moves through the preheater, it undergoes partial calcination, which means that some of the carbonates in the limestone decompose to form calcium oxide, lime. The preheated and pre-calcined raw meal enters a rotary kiln. which is a long cylindrical furnace. The temperature in the kiln reaches around 1450 degrees Celsius or 2642 degrees Fahrenheit. In the kiln, the raw materials undergo a series of complex chemical reactions and sintering, resulting in the formation of small, marble-sized nodules called clinker. The clinker consists of calcium silicates, aluminates, and ferrites. The clinker is discharged from the kiln and passes through a clinker cooler, where air is blown through it to reduce its temperature. Cooling the clinker is important to maintain its quality and prevent the formation of undesirable crystal formations. The cooled clinker is then ground with gypsum and other additives such as fly ash, slag, or pozzolana in cement mills to produce fine powder. Gypsum is added to control the setting time of the cement. Once prepared, the cement is ready for transport to the concrete factory. Because cement is such a crucial part of concrete, cement plant laboratories check each step in the manufacture by frequent chemical and physical tests. The labs also analyze and test the finished product to ensure that it complies with all industry specifications. Now that the cement is ready, it's time to source the aggregate. Aggregate is the most important component of concrete, comprising up to 75% of concrete by volume. When it comes to composition, aggregate is composed of both gravel and sand. The sand is added so the spaces in between the gravel are completely filled, thereby giving the concrete stronger bonding and consistency. A well-graded aggregate, which is a balanced mixture of coarse and fine particles, reduces the requirement of cement, thereby making the whole process much more cost-effective. Now is a great time to talk about the hidden stars of concrete manufacture, the admixtures. These chemicals offer a range of advantages and may be added to concrete to improve its properties. Plasticizers give the concrete greater workability, which refers to its ability to be easily molded and placed without segregation or excessive bleeding of water, allowing it to reach congested areas. Accelerators or retarders are another type of admixture that fasten or slow down the setting time for concrete. Due to the fact that concrete cracks under tension, many chemical additives have been developed to increase the tensile strength of concrete. Concrete may also be strengthened by using fibers made of stainless steel, glass, and carbon. With the raw materials all there, concrete production can finally begin. The first step is to measure the proportions of cement, aggregate, admixtures, and water based on the desired strength and characteristics of the concrete. In fact, concrete mix design is an entirely different discipline dedicated to finding out the right proportions of raw materials in order to reach a target tensile strength. Moreover, building codes have been developed that specify the ratio of cement, aggregate, and water based on the different types of construction. The next step is to mix the ingredients thoroughly to create a uniform mixture. Traditionally, this was done manually using shovels on a flat surface such as a concrete slab. However, nowadays, concrete mixers are commonly used, which automate and speed up the process. The mixing process ensures that the cement particles are evenly distributed throughout the aggregates. Once the dry ingredients are mixed, the water is added gradually while continuing to mix. When water and cement are mixed together, a paste called cement paste is formed. The hydration process generates heat and continues over an extended period, gradually increasing the strength and durability of the concrete. The mixing process continues until the concrete has a uniform consistency. During this step, it's important to check the workability of the concrete. The consistency of the concrete can be adjusted by adding more water or dry ingredients as necessary. Once the concrete is mixed and has the desired consistency, it is transported and placed in its final location. This can be done by pouring it directly into formwork, molds, or by using specialized equipment such as pumps or conveyors. During the placing process, it's important to avoid segregation, which is the segregation of coarse aggregates from the rest of the mixture. After the concrete is placed, it needs to be properly compacted to eliminate any voids or air pockets. This is typically achieved using vibrators or by mechanical means such as tamping or rolling. Compaction ensures that the concrete is dense and has good strength and durability. Once the concrete is placed and compacted, it needs to be cured. Curing is the process of maintaining adequate moisture and temperature conditions to allow the cement to hydrate and gain strength gradually. This typically involves keeping the concrete damp or covering it with curing membranes, blankets, or plastic sheets. Curing can last for several days or weeks, depending on the type of concrete and the desired strength. After the concrete has cured sufficiently, various finishing techniques can be applied to achieve the desired surface texture and appearance. This can include techniques such as smoothing, leveling, troweling, or applying decorative finishes. Owing to its versatility, cement is the most widely used construction material.
A lot of energy is required for the production of cement. The energy requirements alone are equivalent to approximately 55,000 four-person households, comparable to the needs of a medium-sized city like Halle. For years, we have been working to reduce energy consumption. Not only for reasons of cost, but also because it is important for us to deal with our natural resources sparingly and keep CO2 emissions as low as possible. At 20% below the average, the energy consumption of the Rüdersdorf plant is now among the lowest of the Cemex group. The kiln has been optimized to such a degree that energy requirements can hardly be reduced any further. We therefore use secondary fuels to further reduce the consumption of primary fuels such as coal and oil. Today, 75% of our thermal energy is obtained from secondary fuels, mainly fluff, a material produced from recycled industrial and household waste. Meat and bone meal is also used as a fuel. Meat and bone meal are special treated remains from rendering plants. Dried sludge is also used as a fuel. The resulting ash can be reused immediately for clinker production.